Lecture corresponds to Chapter 70 in Guyton and Hall. It is entitled The Liver as an Organ. The liver is a very important organ in our body. It has over 500 vital functions in your body. About 200 of them are just metabolic. So the liver serves a very important role in our bodies. You already know of one function in digestion, since this lecture follows the lectures on the GI system. It produces bile. Today we'll discuss a multitude of the other functions that the liver serves. We'll be looking at the anatomy of the liver, the blood flow, the various metabolic functions, other functions, obviously going over again its role in digestion, and then we'll also be looking at the excretion of bilirubin by the liver and how we can use it diagnostically. So as an overview, you all should know that the liver is considered to be the largest visceral organ in our bodies. It is found in the upper right hand portion of the abdominal cavity, just below the diaphragm, on top of your stomach, which here's your stomach obviously there, above your right kidney and the intestines. It is perfectly centrally located because of its role in metabolism, the absorption of nutrients and vitamins from the GI system goes right to the liver, so the liver could be there to kind of figure out what to do with it. The liver is also a good location to deal with toxins that have, say, come from the spleen or what you have also absorbed in the GI tract. The liver has 4 lobes, of course, which you know from anatomy. The right and left lobe, and then you've got the caudate lobe, which is by the vena cava, and you have the quadrate lobe, which is by the gallbladder. The largest lobe being the right lobe. The lobes are made up of thousands of lobules. Now, the hepatic lobules are the functional units of the liver, and they kind of have a hexagon shape. So if I kind of draw a thing around here, it's like a hexagon shape. And they're arranged around a central vein, which you see here. Here you only see a portion of the lobule, so you have the central vein. Now remember, when we discussed bile production, bile was produced by, I said, parenchymal cells. Well, the hepatocytes, the primary cell type in the liver, are hepatic parenchymal cells. These cells which you see here on this side of the screen or over here, those make up what we call cellular plates. Now these cells, one of the things they do is make bile, and when they make bile, they secrete it, and you can see it better here, into the bile canaliculi, kind of literally meaning little bile canals. They empty into the bile duct, which then eventually empties into the, or it can be stored in, or go through the cystic duct to the gallbladder and be stored, or eventually go out through the common bile duct, and then eventually into your intestine. And you see kind of right here, here's a bile duct. You notice at each end of these, you kind of have a triad. So you have a bile duct, you have a hepatic artery, which you see over here, and you have a hepatic vein. So we're going to talk about the significance of the hepatic vein, or specifically the hepatic portal vein and the hepatic artery. So blood is going to be entering the liver lobules from the hepatic artery and the hepatic portal veins. The hepatocytes are going to be doing their thing, picking up glucose, nutrients, whatever. Eventually, they'll empty into these central veins. Now, you'll also notice that in between these plates, you have sinusoidal capillaries. So in the liver, the type of capillaries we have are sinusoidal capillaries, and for those Canadians, we'll say capillaries. So the sinusoidal capillaries are the type of capillaries we have in the liver. They have kind of wide spaces. They're also called discontinuous capillaries. So they have incomplete basement membranes, which is kind of important when you're talking about big stuff going from the hepatocytes out, or things like that. I mean, it's good to have so you can filter a lot of large proteins, red blood cells, things like that. The sinusoidal capillaries are lined by Kupffer cells, which you're well aware of. You've heard of Kupffer cells before. Those are macrophage, so we'll discuss their role in a little bit. You'll also notice this space right here. These we call the spaces of Diess, which I'm probably pronouncing wrong. They're also called parasinusoidal spaces. So they're near the sinusoidal, or the sinusoids. These are pick up excess fluid that from the sinusoids, because the sinusoids are kind of leaky. So a lot of extra fluid will fill up these spaces of Diess, and it'll empty into lymphatic vessels, which you see here. Here's a lymphatic vessel. So we'll also discuss lymph flow in the liver today. Now let's discuss that blood flow. I had mentioned that the blood comes into the liver through hepatic artery and the hepatic portal vein. So it's getting more than one blood supply. Now the total blood flow in the liver is really large. It's about 27% of your resting cardiac output. So it's a fairly good amount of blood going to the liver at one time. So, and you notice we have here that most of that liver blood flow comes from the hepatic portal vein. So 75% total blood going to the liver is through the hepatic portal vein. That is bringing deoxygenated blood. That's why you always color it in blue. Well, that deoxygenated blood is filled with nutrients and vitamins, which you just got from the GI tract. You just absorbed all those nutrients. The liver gets the first crack at it. You also, though, have bacteria, but hopefully the bacteria will be caught by those Kupffer cells. You also have to get oxygenated blood to the liver, so that's coming through the hepatic artery. So the hepatic artery is delivering the oxygenated blood so the liver cells can get their oxygen and be happy, but it also gets a large amount of blood from the hepatic portal system, because it's the role of the liver. One of the major roles of the liver is our metabolic functions, which involves trying to maybe say store vitamins, deal with the absorbed nutrients like making glycogen, things like that. Now when the blood enters those sinusoids, they're going to do, this is kind of a review, so you kind of saw it in the earlier slide. Now I just want to see if I can pull out some answers before we write them down. So blood is going to enter the liver sinusoids coming from the GI tract. So we just absorbed a lot of good stuff. So I just had a large carbohydrate meal. What's the digestion products of carbohydrates? Monosaccharides. So specifically the major monosaccharide that we'll absorb in the GI tract will be glucose. So something like glucose will go to the liver. What's the liver going to do with it? Hey, probably maybe make some glycogen. So you get things like glucose. You get your fats, any of the absorbed nutrients that you got from the GI tract, or protein products, things like that. That's going to go to the liver. It also will bring in vitamins. So you've got some vitamins. So the liver may store some of these vitamins. Also bringing in some bad stuff, bacteria. And well, this unconjugated bilirubin is a big breakdown product from red blood cells. Now, red blood cells were broken down in the spleen, and that results in bilirubin, and bilirubin will be brought to the liver, and in the liver we're going to do something with that unconjugated bilirubin. Now up at the top of here we talk about blood flow to the liver. I said blood flow to the liver is pretty good. It's about over 20-something% of your total cardiac output. And if you remember from Physiology 1, your flow equation, Q is flow, and if you want to say total flow, that would be your cardiac output. That is equal to the change in pressure over resistance. So remember this from Physio 1, that's the flow equation. Told you it's very important to not forget that equation. So if you know the flow equation, you can tell me, well, what things can influence flow? Well, if I change the pressure gradient, if I increase pressure, I can increase flow. If I decrease pressure, I could decrease flow. The resistance is on the bottom. Well, if I increase resistance, I will decrease flow, and vice versa. Now, I'm going to tell you that the pressure difference between the portal vein and the hepatic vein is only 9 millimeters of mercury. That's not a lot of pressure difference. So how come you have so much flow? So if you remember the equation, you'll be able to answer the question. So if I don't have a huge pressure difference, why do I have so much blood flow? It's because of this. I have a very low resistance in the liver circulation. So that's an important concept to understand. Then the question is, how can something like cirrhosis or a large blood clot affect flow? Well, if I have a blood clot, that will definitely increase resistance to flow. Cirrhosis, with cirrhosis you can have scar tissue that contract around the blood vessels, which would increase resistance. So if I increase resistance, that could decrease flow. Well, also what may happen is something called portal hypertension. Portal hypertension results when pressures in the hepatic portal system start to increase, usually when it starts to get over, and it doesn't seem like a lot, over 10 millimeters of mercury or more. So the pressures in the hepatic portal system are really low, but when they start getting high, what's going to happen is it leads to what we call portal hypertension. The different causes of portal hypertension could be like blood clots, cirrhosis. Now cirrhosis, people automatically assume, oh, cirrhosis is because people are alcoholics. No. Some people that are alcoholics can have cirrhosis, but viral hepatitis can lead to cirrhosis. Something called non-alcoholic steatohepatitis and non-alcoholic fatty liver disease. Now you may see the, say for example, non-alcoholic fatty liver disease in people who are type 2 diabetic, obese, things like that could lead to cirrhosis. So don't automatically assume someone's got cirrhosis is because they're alcoholics. But all of these could lead to what we call portal hypertension. And over on this picture, you can see the different consequences of portal hypertension. People get marked ascites, and we're going to show you a picture of what ascites is. See the kind of a lot of fluid leaking into the peritoneal cavity. Spleen can become enlarged. You get esophageal varices, hemorrhoids. The portal hypertension is a fairly significant thing to have, and it's does not have a good, relatively good prognosis. Now the liver, because it has such good blood flow, it also has a fairly amount of blood in it at one time. So they say about 450 mils of blood is in your liver under normal conditions. The volume can change. So volumes can increase, but this is not a good thing. This will start to increase generally if you're right. This is, remember, your abbreviation for right atrial pressure, which is also referred to as your central venous pressure. Remember, it's the pressure right at the junction where the vena cava meet your right atrium. That increases a lot. Things kind of back up, and liver blood volume can increase to kind of accommodate the blood that's kind of backed up. The liver can serve as a specific venous blood reservoir, which would be important, say, if you're hemorrhaging. Since the liver has a good amount of blood, some of that blood can be diverted out into the arterial system to help with blood loss. Remember we had mentioned about those spaces of Dice. or those parasinusoidal spaces. Well, the liver, because of the sinusoidal capillaries, have a lot of fluid that leaks out of those capillaries, and so the fluid leaks into those spaces of Dees, and that enters into the lymphatics, and they say about a half of your total lymph in your body is formed in the liver. That's a lot. So what happens if you have, say, high pressures in the hepatic veins? A lot of excess fluid is going to be forced across the peritoneal cavity, into the peritoneal cavity, across the serosal surface of the liver and the viscera, and you can end up with what you see here, ascites. And so this is a really good picture from Netters. They say you get sweating of fluid from the surface of the liver, and it accumulates right there in the peritoneal cavity. So this is an example of ascites, which could happen if you've got portal hypertension. So you can have a blockage of blood flow, say a blood clot, or cirrhosis too. You'll get ascites. Now, what about people who have significant cirrhosis or hepatitis, where they've lost significant amount of liver function? Well, they can have a liver transplant. Well, the liver cells are pretty good cells in that people, say for example, we'll go back a little bit. People who drink a lot can end up having cirrhosis. Well, prior to getting cirrhosis, they are, damaging their liver, damaging their liver. Your liver has a remarkable function of regenerating itself. Well, once you get, because this is a little review from general pathology, is hepatocytes are examples of stable cells or quiescent cells. Remember, you have three different types of cells. You have what we call labile cells, which continuously cycle like your epidermal cells. You have non-dividing or permanent cells like neurons, cardiac myocytes, and you have these quiescent or stable cells. Well, these cells can re-enter the cell cycle if you have an appropriate stimulus. So you can try to regenerate the hepatocytes. Well, we can use that to our advantage if you get to the point where you must have a liver transplant. Say your liver is so bad, it's so cirrhotic, and once you get cirrhosis, that's kind of, you can't go back. It's completely scarred. They would have to have a liver transplant. Well, what is becoming a little bit more common nowadays are live liver transplants, or live donor liver transplants, in which a living donor donates part of their liver and to a recipient. And what's really interesting is that I have read where you can have up to about 70%, but I think that's pushing it. But you can donate up to about 60-70% of your liver and be able to regenerate that liver. And you can give it to the patient. And the patient's not getting a full liver, but within the donor, that liver will regenerate, and what will happen is you'll get full size, the volume of the liver, and full function. So they say about, usually when you do a liver transplant, they say about 55-70% of that right lobe of the liver is cut and transplanted into a donor or a recipient. The donor will have 100% function of the liver within 4 to 6 weeks. The size of the liver will be back to its original size a little bit longer than that. The donor will have full function and their appropriate size. It'll take a little bit longer than in the donor itself. Okay, the donor itself. So that's kind of a good thing. So the first ever living donor liver transplant was done on a 2-year-old, and her mother donated her liver, or part of her liver, to the girl, and the girl survived, which is kind of a nice thing. It's still it's a risky procedure, but it's a lot better than waiting around for a cadaver. As long as you have compatible blood supply, the donor is really healthy, you can do these live donor transplants. What's interesting is from dog studies, and obviously doing it with humans, is when they transplant a liver from one size dog to another, the liver automatically adjusted its size to fit the body size of the recipient. So if you transplanted a portion of the liver to a large dog, it regenerates to the size that was appropriate for a large dog. If you donate it to a smaller dog, it regenerates to the appropriate size for a small dog. I have no idea how it does that, and I think it's going to be a while before they can figure that out. But there are a lot of growth factors that are involved in liver regeneration. There's other factors that are involved in probably getting everything to kind of stop once you get to the appropriate size. Things like transforming growth factor. Beta may be involved in stopping that growth when it gets to its appropriate size. A growth factor called hepatocyte growth factor is thought to be a major one in the regeneration of the liver. Now the Kupffer cells, we had mentioned the Kupffer cells. Now Kupffer cells, which I like this picture here, they're macrophage. Remember, macrophage are kind of large multinucleate cells. These line the sinusoids, which you see, here's the sinusoids here. Here's some Kupffer cells. Well, they're there to do a lot of things for you. So they're kind of monitoring what's coming in. They're going to engulf any bacteria, viruses, remove any damaged red blood cells that were from circulation. They're going to attack things that are foreign. So they're a good part of the immune system. They say that Kupffer cells, they work so well that less than 1% of the bacteria that came through the system, the liver, makes its way into the systemic circulation. That's pretty good, considering that we're ingesting bacteria all the time. Now, the next part of the lecture covers the different functions of the liver. And a lot of this is review, and you can read this. It's all written out for you in your notes. So I don't want to read to you, so I just want to emphasize some of the major functions of the liver, and I'll let you read through them. Now, the liver has over 200 metabolic functions. So in Biochemistry 1 and Biochemistry 2, I'm sure you learned about all these different pathways, and a common theme is like, oh, takes place in the liver, takes place in the liver, takes place in the liver. They weren't lying. So the liver makes glycogen. It is very important in maintaining your blood sugar. So if you blood sugar drops, you can break down the glycogen in the liver. You can make glucose from scratch, your gluconeogenesis. Major location for metabolism of fructose and galactose. So those are your other monosaccharides, where they're dealt with in the liver. So the liver does a lot of stuff with carbs, carbohydrate metabolism. In Biochem 2, you learned about fat metabolism and the role of the liver in fat metabolism. So it was important in beta oxidation. It was the site where you make ketone bodies. Remember, the liver, though, can't use ketone bodies, but it makes ketone bodies when you're breaking down a lot of fat. It can make fat from ingested proteins and carbs. Anything extra, let's just make fat from it. It makes cholesterol, so it has a very important role in your fat metabolism. Biochem 2, you should also learn about protein metabolism. So it removes the amino group from amino acids. It will form urea for removing of ammonia, because otherwise if you deaminate amino acids and you don't deal with it, It's not a good thing. So you have to convert ammonia, which is very toxic, to urea. It makes a lot of plasma proteins, the globulins, the immunoglobulins involved in immunity. Albumin's a big one. So what do you remember hearing? Albumin does a lot for you. Do you remember in the material for the first test this trimester what albumin did, or one of the roles that albumin did? Remember, a lot of your hormones bind to albumin. So like thyroid hormones can bind to albumin. Some of your steroid hormones bind to albumin. So it's a transport protein for some hormones. It plays a major role in maintaining osmotic pressure in your blood. The liver also plays an important role of converting amino acids to other things. So remember, you can take glucogenic amino acids and make glucose from it. So that's like an example and that involves this interconversion of amino acids with other compounds. Now, other one is its storage of some vitamins, such as or most people they go, okay, I always remember that the liver stores fat-soluble vitamins. Yeah, it's true. So vitamin A is fat-soluble, vitamin D is fat-soluble, but here's one that is not fat-soluble. Vitamin B12. That's a kind of important one. It's appeared on boards before. Is vitamin B12 is a water-soluble vitamin that can have significant amounts stored in the liver. So I want you to kind of make sure you remember that. Vitamin A, definitely good store for in the liver. The liver also can make vitamin A from beta-carotene. I always kind of talk about the story of vitamin A toxicity, and you probably learned that in biochemistry too. You'll learn it in nutrition. You can have adverse effects of taking too much vitamin A. So knowing that vitamin A is stored in significant quantities in the liver, it's kind of an interesting story of the people that were up in the Arctic, and they made the sad mistake of eating polar bear liver. And there are stories of these explorers that ate polar bear liver, and they ended up with vitamin A toxicity, and it kind of made them go crazy. So you can look up the different things that vitamin A toxicity can do to you, and one of them is to make you go crazy. That and go in Parker, but that's another story. The vitamin D we talked about earlier in the trimester. You have good quantities of vitamin D3 stored in the liver. Now, that is cholecalciferol. So remember, cholecalciferol was a product that was made from as a result of exposure of your skin to UVB radiation. So you have the cholecalciferol, which is not the active form of vitamin D, but this is where we store this in the liver. Now, when we need to, in the liver, we can convert that to 25-hydroxy cholecalciferol. That occurs in the liver, and that circulates in the blood, but that doesn't have as a long lifespan as cholecalciferol. The liver also is a good source of iron. So growing up, Mom always said, eat your liver because it's a good source of iron. She was right. The liver is a good source of iron, and they say it serves a role as a blood iron buffer. So if you need a little bit more iron, it can release the iron. Remember, it's stored as ferritin, but it's going to be transported in your bloodstream as transferrin. The liver has other functions. So most of your clotting factors are formed in the liver. Not all of them, but the majority of your clotting factors are formed in the liver. So there's a real important role in detox. So when you're drink alcohol, major location where it's metabolized is in the liver. A lot of drugs are detoxified in the liver. It does a lot of plays a major role in the endocrine system in that it inactivates a number of hormones or alters them in one way, shape, or form. And also remember that excess calcium can be removed via bile. So remember, bile is made in the liver, and it's made in the liver, main functions for digestion, but we can remove extra calcium in the bile because that's a component of bile. We also, bile is composed up of cholesterol, so you can get rid of extra cholesterol that way. It has these two, remember, bile salts and lecithin. Those are the two real important parts of bile that serve its role in digestion. And what was their role? They helped you to digest fats by emulsifying the fats, making the surface area, increasing the surface area for the lipases to work on the fats. Now, bilirubin is also a component of bile. Remember, that is a breakdown product of red blood cells, and bilirubin we need to get rid of, and it's predominantly going to be in bile, and we're going to show you kind of how we get rid of it and how we can use bilirubin as a our clinical diagnostic tool. So here's a picture that depicts in the red blood cell. You just love how my picture just cut it in half. The red blood cell is degraded in the spleen, my beautiful picture of a spleen. In the spleen, the red blood cells are destroyed. Now, the bilirubin is formed from the breakdown of the heme ring in the red blood cell. The bilirubin is what gives bile the color. That kind of greenish, yellowish color is because of bilirubin. In the liver, or actually before we get to the liver, the bilirubin that's released from the breakdown products of the red blood cells in the spleen is released as what we call unconjugated bilirubin. This is not very soluble. So albumin will act as a carrier protein and transport it to the liver. Now, in the liver, it is conjugated. Now, conjugare is a Latin verb which means to join together. So the conjugation of bilirubin means I'm going to add or join something to bilirubin, and what's added to it is something called glucuronic acid. Glucuronic acid is derived from glucose. It's a sugar acid of glucose in which a hydroxyl group of glucose was converted to an acid, a carboxyl group. Well, glucose is polar, got a lot of hydroxyl groups. You add a carboxyl group, which is negatively charged at physiologic pH. You add a charge to it that makes it even more polar, and by conjugating bilirubin with glucuronic acid, it increases its solubility quite a bit. The bilirubin, or this conjugated bilirubin, is pretty soluble. Well, this will be excreted by way of your bile salts to eventually go into your gut. And in the gut, you have some of that will be broken down by the bacteria line your gut to urobilinogen. Urobilinogen, some of it can go filter back to the liver. Eventually, we'll get rid of it. Some of it can be converted to urobilin and excreted in your urine, to kind of give some of the color to the urine. Usually it shouldn't be a lot of color to the urine. It also can be converted to stercobilin. I just can't even say it. Stercobilin. This and this help to give feces their color. That dark brown color comes from the breakdown products of bilirubin, such as urobilinogen and stercobilin. If you have say a block in the bile duct, complete bile duct obstruction, you will not get bilirubin in the intestine. So what's going to happen is you will not be converting this to this. What happens is then your feces will not be the dark color, because that dark color, brownish color, comes from the urobilinogen and stercobilin. So you get more of a clay colored stools if that happens. So that's kind of cool to know. Now, other terms that you may hear maybe in lab diagnosis for unconjugated bilirubin is they call it indirect bilirubin. This one is called indirect bilirubin. Conjugated bilirubin is called direct bilirubin. The reason why they gave those names comes from some diagnostic tests they use. If they're trying to test for unconjugated bilirubin, this is not water soluble. So in order for it to react with the dyes in the reagent, they have to add alcohol to it. So they said, okay, it's indirect. This is water soluble. That will react to the dyes in the reagent directly. So that's why they call it direct bilirubin. So that's just you may hear those terms. Now they can use or look at the measurement of unconjugated bilirubin and conjugated bilirubin in clinical diagnosis. So one example would be if someone has jaundice. So I like this cartoon. Your jaundice makes your teeth look whiter. Now jaundice makes people have a look kind of a yellowish skin. The whites of their eyes look yellow. It's because of the retention of bilirubin. There's a number of different causes of jaundice. Now jaundice is not a disease, it's a symptom. So how you would get jaundice is if there's any disturbance in your ability or in your production of bilirubin, which is this is something that normally happens. I mean, we have to produce bilirubin because you break down red blood cells. But you need to be able to produce bilirubin, but then get rid of it. So if you have a problem getting rid of it, or you overproduce the bilirubin and don't have enough time to be able to excrete it, someone will become jaundiced. So a good example would be something called the hemolytic jaundice, where someone is breaking down red blood cells too quickly. You break down a lot of red blood cells too quickly, the liver will not be able to conjugate that bilirubin quick enough. And so a lot of your bilirubin that will be measured would be the unconjugated bilirubin. So you would see that more in the hemolytic jaundice. With obstructive jaundice, think of what it tells you. Something's obstructive or obstructed. If I had a blockage in my bile duct and I can't get rid of bile, what's going to happen is I've conjugated my bilirubin, but I can't get rid of it, but I have a hard time getting rid of it. But I measure in the intestines, via the intestines, most of the bilirubin that someone measures in their blood will be conjugated instead of unconjugated, because I can convert it in the liver, but I just can't technically get rid of it. So you're going to have a lot more conjugated bilirubin. Alright, that's the end of the lecture. So it's a relatively short lecture. So if you have any questions, all you have to do is ask.